a bit later, so please welcome our speaker.
Alexey, thank you. Thank you for introduction. Yes, I think we're going to start. We are going to discuss today a topic of text-to-video generation. Maybe a little bit text-to-image, but it's not the main theme today. So main theme of text-to-video, of course. And I talk about the current state and challenges of that field. We talk a little bit about the diffusion. We talk a little bit about the main question of this field. Does do this model do these models tends to Volt models, and what does it mean at all? Talk about the Kandinsky 4.1, our last model to generate images and video, and I give some intuition and some applications of that models. So let's start. I start from not from the Kandinsky. I start from the landscape of that field during four previous months, actually, and the prominent paper, the prominent product release. First of all, the first one that I would like to discuss is ChatGPT for image generation. Raise the hands, please, who tried this model. Okay. Here you see some pictures that generated by this model, and you may see the really huge prompt on the left of the slide, and you see the generation of the image like by this prompt that is on the right center of the on the center top of the slide. So what we see? We see that we may feed to this neural network the really huge instructions, and the neural net is perfectly follows that instruction. The neural network write the text on the picture, like following shows the good visual quality, text following and prompt following, and so on. Moreover, we can edit the image just using one model, not only generate image, but edit too. So you may, for example, give an image as an initial image, like ask to change this image, for example, add some background, for example, with photo, with, I don't know, home, cozy style, and so on. Then you may like invert this cat, add the coin, change the coin from euro to ruble, and so on. So you may, like feel image like a text, because you have like a huge ability to change the image just using the text. That's great, and this really really important. But why it's so prominent from my point of view? Because that the first architecture, first public architecture that everyone can try, that that consists only on one model, the transformer, that models the text tokens and image tokens as one sequence. So it's not two models like usual, like flux context, for example. when you have like large language model that represent the text, and second part, diffusion transformer, for example, or UNet that generate the image conditioned on these embeddings, on the embedding of text. That's the usual scheme. But ChatGPT for all image generation is not like that. It's union model. So it's one model. That's really great. And we don't know actually how it works, what the details, because researchers and engineers did not public the technical details actually. But there is a plenty of work from the past year that is similar. The principle is quite similar. For example, one of all is transfusion. The key idea of how we can unite the visual part and the text part is the follows. We can take the autoregressive transformer that works with text like in usual, like an autoregressive setup. So predict the probability of the next token by token, but it works with image not in the autoregressive scenario, but in the diffusion scenario. So it denoise patch by patch, so embeddings that represent the patch by patch, and models the diffusion process. So predict the next step of the diffusion process, of the reverse diffusion process, in simultaneously full picture. And after that, in the same time, the text, so token by token and so on, they use for training the combined loss, for loss of cross entropy from language modeling, and the diffusion loss as a Messier actually from the DDPM. We will talk about the DDPM a little bit later in details. So that's like high level idea of how it works and how the ChatGPT for image generation can work. So one more time, why it's so great idea? Because from one model, we aggregate the discrete data such as text and embedded text tokens, and the continuous data such as the pictures, embedding of the pictures. And this is a great principle, and it works quite better than, for example, when you discretize the image. So for example, DALL-E the first worked from 2021. We will talk about it later. So that's great. Second prominent work from the previous 4 months is the VO3, from my opinion. Raise the hands again who try VO3 or see some video generations. Not so many actually, but maybe you see some like from Telegram, in Telegram, some generations of the, I don't know, from the babushkas and so on. No? Okay. So the VO3 is the video generation models that is developed by Google, actually DeepMind. And that is public model too, that is really had the really great quality. But why so prominent, from my opinion? Because they generate not only the visual sequence, so the video, but they can generate audio sequence synchronized with video sequence. Again, with one model, inside one diffusion transformer, not separate for video and audio, but just one for one diffusion transformer for all tasks, for generating the video and generating the audio. You can see the video here, how it works. Is it good to hear or not? Okay, nice. So again, you had just one prompt, not two, not three, not separate modules and so on. Just one prompt to generate video part and the audio part. Just one prompt again. And you can see the lip sync there, but it's like internal property of the model. You may I show some another examples of the generations. One more time. Sorry for the sound. It's translated from my MacBook. So again, this is generation from one model, not two models. And they presented, I mean, Google presented the View 3 at May. Now it's July. And we see on there is a great video arena where you can see the whole top image generation models, video generation model, and so on. And you can see that there are at least four, oh, here, at least three, not four, at least three models from China, actually. It's great for China, I think. That is better than VO3. For example, in image to video task. For the, I mean, you have initial start frame and generate a video. That shows how quickly researchers all around the world developed such an architectures. So we see the CDance from ByteDance seed, we see Hilo from Minimax and so on, a lot of architectures. And it's that's generation actually from I don't know from what from CDance or Hilo, but it doesn't matter actually. It's from Telegram too. But you see that the main focus of the current research here is to teach the model reproduce the physics of our world, you know, to reproduce the correct generations like you just, I don't know, to have a camera and do some shot of that camera. So represent the physics is the main goal of it. And for example, in CDance, in ByteDance research, they solved this problem by adding the RLHF procedure after the training, after the pre-train, after the SFT, and they had three reward function. It's the foundational reward model, it's motion reward model, and aesthetic reward model. And they had three reward functions. They optimize the base model in respect with reward and see huge improvement of the quality of the generation in aesthetic, in movement, in prompt following. That's great. That's great because it's kind of similar to how we train the large language models. Here we see the same effect. RLHF, SFT had a huge give a huge boost for the video generation and image generation too. But I see that, and I said that it's not ideal till now. There are a lot of hallucinations of such a model. For example, you see the Sora, but it's not actually the modern model, but it's a generation from the December 2024, so half an year before. So not so modern, but not so old actually. You see the like usual hallucinations of the video and image generation models here, like, you know, when you have a lot of small objects, small objects or small animals, for example, people, there is some collision between them. That's the common. And such problems can be solved by RLHF, for example, and training the good reward function. I talk about the DALI. DALI the first was published at January 5th, or January 5, sorry, 2021, it was autoregressive model like that. From text tokens to image tokens, they use vector quantized via for represent the image. And when you quantize the image, you lose the information. That's why transfusion is better, as I said. But see how the progress, how we change the and how what the big progress we have during only 4 years. So state of the art of 2021 was that is capybara sitting in the field of sunrise, and state of the art of image and video after 4 years after that. So 2025, that's quite different, because now we see at the, like, we see at that generation and see, for example, sorry, we seeing the generations and try to find some artifact that is not, for example, coincide to our expectations. But it's like huge progress during 4 years, and the progress is increased, as I told, and on the, for example, video arena benchmark. Okay. One more thesis. During the progress start, I think, from 2014, when generative adversarial networks was represented by Jan Goodfellow, the famous and prominent work. After that, the generative architecture for generating, I mean, images, videos, starts to developing quickly. But and after that, there are a lot of architectures that was invented by researchers. For example, as I said, generative adversarial networks, variation autoencoders, flow-based models, autoregression, as it was in DALL-E, as it is on transfusion, and I think ChatGPT for image generation, and of course the diffusion. Diffusion now is the state of the art. Despite of some architecture, good architecture is autoregressive. For now, diffusion and some, like, the similar models like flow matching are the state of the art approach to to modeling the, for example, generating of the video, generating of the image, of the 3D, all visual modalities. And we talk a lot about, today we are going to talk about diffusion in focus. If we talk about the Kandinsky, we developed the architecture. We are developing, actually, the architecture quite long time. We start from 2021. We inspired from DALL-E, actually, and after that we was going to developing the Kandinsky. The first two models were autoregressive 2. It's Malevich and Kandinsky 1.0. After that, all models are diffusion, and latest one are flow matching. And I talk about that a little bit. So our last family of models, Kandinsky 4.1, and this is the models for generating images and videos, as well as image to video, text to video, and so on. All manipulation to generate a video and all initial conditions. Let's talk about the diffusion a little bit. So the main principle of, the main principle of and state-of-the-art principle of generating a video for now. I think the sound is finished, but it's for sound. Okay. So as I said many times during my presentation, now we are living in the era of video generation models, as well as the race of large language models, of developing of large language models. In video generation models, we have the same picture, such as in LLMs. I think the race was started at when Sora is released. Sora was released on February 15, 2024, so 1.5 years before. And after that, a huge amount of new approaches, new architectures, new public releases, new research were presented. We had, like, I don't know how many video generation models we have for now. So it's more than, I think, more than 50, I don't know, a lot. And all of these models are good. And let's say in a certain cases, for example, and so on. I like the move again architecture and move again paper from Meta because they were the first paper that was presented and written and the technical details that was the first on video generation. Now we had a lot of papers, not so many in compared to LLMs, but like a little bit we have. But Move Again was the first paper with technical details. We see that, for example, to create the flagship model, they was need around 400 million pairs of text and videos, scenes of text and videos. They need more than 6,000 H100 for training the flagship model. And we approximate how much resources and data we will need to create the model that will be similar or maybe better than that model. After that, there are plenty of works published, such that Hunyan video from Tencent, China. One is a really nice model. And I think the one model is the better model in open source till now. 1.2.1 especially. From Alibaba, that's really nice. And almost all open source solutions, moreover, some startups, like a Higgsfield AI, for example, is based on the one. So that's a nice model. But let's talk about the difficulties, actually, in compared to LLM, because LLM is like more well-known field. Video generation models and video generation is the young field, as we see, because it starts from 2023, 2024, so like 1, 2, maybe 3 years, and that's really that's all that we have. So no scaling laws for that model that can be trusted. In compared to LLM, when we had plenty of work on scaling, like Chinchilla and so on, started from Chinchilla in 2022, we had really plenty of work for that. How we can, what does it mean scaling? Scaling means that you had the small models that is not good, but good for the small models. The question is how you can produce, how you can train the big model to increase the quality. How many data you need, how many, tokens of the data, yeah? How many resources you need, and so on. So that's questions. There are a lot of, for LLMs, there are a lot of science around this team. In video generation, not so many. So we cannot trust. We can trust by ourselves. So we need to reproduce, to produce such an experiment. That is really important. Moreover, we just, as I said, we had just a few good quality open source solutions. I think only one that we can based on, it's one. It's really good. And another one, the computational complexity is higher than an LLM field. Why? Because you can see on the last row in my table here. And in compared to LLMs, where the context of the model is character, I mean, like an average, not all large language model has a different context, and that's okay. Yeah, I mean an average. Average context, I think it's good context is like 128,000 tokens is nice. There are a lot of models that has the bigger context. For example, Gemini. Gemini has like the flagship model. I mean, has 1 million tokens, 500,000 tokens, doesn't matter. Little bit bigger, but that is an average. For example, our GigaChat has we had the version with how that works with such amount of tokens. But if you don't, I talk about the variation of the encoders a little bit later, but intuition is that before you are going to train the diffusion transformer that can generate video, you need to compress the video, because you cannot work with video as is. It's really, really huge amount of the data in one video. You can like approximate in your mind. If you, for example, had a full HD video, it's near 2,000, 1,000 pixels, so 2 millions, a little bit less. You had, for example, 10 seconds to generate, multiply by 10, and by frames per seconds should be at least 24. Because if you had the less of frames per second, you will not see the video. You see the like frame by frame, like not continuous picture. You understand? So if you multiply by 10, by 24, by 3, because red, green, blue, you see that in the 10-second full HD video is more than 1 billion 1 billion integers, for example. So the huge context, it's really huge context. So you need to compress the video. But if you don't compress on the time and compress only on special access, you see that your video is 1 million tokens. So you can compare with large language models. So here 1 million tokens, here 100,000 tokens, so 10 times less. So that's the intuition. That's not like, it's approximate number of tokens, but the computational complexity in video generation is much, much higher, much higher. If you don't like use the advanced variation of the encoders, for example, that compressed, the really more effective. Okay. So that's the topic of the difficulties of the current landscape. What about the diffusion? Diffusion is as I said, the state-of-the-art method for generating the images and videos. And the principle is the following. I said just a little words about that because there are a lot of scientists there. I see that I think told about the diffusion in more details. But one more time, diffusion consists of forward diffusion process and reward diffusion process. In the forward diffusion process, you add the noise simultaneously on the data. In reward diffusion process, that's actually what diffusion models do. You train the model to delete the noise, to remove the noise, step by step. That's how images and videos generated. So you start from the Gaussian noise, multivariate Gaussian noise, and step by step denoise it to the images or videos, doesn't matter actually. Video is the sequence, just a sequence of the frames of the images that is consistent all the time, of course. So one more time, in the forward diffusion process, you add the noise, like here, like I see here, and you, for example, if you have a Gaussian noise, you may parameterize that, not parameterize, but write the equation of how you can receive the next step, for example, x2 from x1. You had the sequence of the coefficients, And idea is that you give a small amount of noise and multiply the initial image, for example, x1, on some coefficients less than 1. Step by step, you are going to the total, to the approximately standard normal Gaussian distribution, Gaussian noise. And you see the equations there, as I said, minutes here. So you may so that's how you can receive xt from xt minus 1. Alpha t is just a constant coefficients there. Epsilon t minus 1 is a Gaussian noise. You may write this equation and you may receive, after that, you may receive, so you may like take a consequence that xt can depend only on x0 here. So you may receive xt directly from x0 by using the another coefficients, but another, I mean, I don't write it. I write. It's in the following. That's the forward diffusion. And you see that if beta t is the coefficients is less than 1, so alpha t hat is the like product of such coefficient. A lot of coefficients is less than 1 tends to 0, of course, production of it, I mean. So this is alpha t is tends to 0, but this one is tends to 1. So xt is tends to Gaussian noise, of course. That's quite simple. So you really tends to Gaussian noise here. But your main goal is to reverse this process, start from total Gaussian noise, independent, I mean, and step by step denoise it to initial image. There is a really good theory beside of that. Besides of that, but you know, you can modeling. You actually just need to model the conditional probability. If you model the conditional probability of such, so x t minus 1 in condition of xt, if you can model it, so you may sample from the distribution and start from Gaussian noise, receive the next images in such a process. And nice, that's actually the really beautiful mathematical theory, or in my opinion. You may see on this process from another side, from different side of view. You may see on the stochastical differential equation. You may see on this process from the theory of latent variables and so on model. And if you, for example, see from the latent variable model view, you may just like take the take the loss actually of this process, and this loss will be the follows. It has the like good intuition behind of that. So in each step, you had your neural network, your neural network that you trained. It's maybe I talk a little bit later about that, but it can be a UNet, for example, or diffusion transformer. Doesn't matter. Why UNet or diffusion transformer? Because you see in UNet you have the dimension of the input the same as the dimension of the output. That's the main reason. In diffusion transformer too. So you may construct the diffusion transformer in such a way that diffusion transformer input wait for the input and gives to the output the same dimension of the tensors here. But diffusion transformer is better in terms of scaling. You understand? Yeah, UNet and convolutions scales not so good. Diffusion transformers, because the transformer scales better. The main reason why now diffusion transformers is much more preferable architecture, and a lot of works use the diffusion transformers in compared to UNet. But again, go here. So you have the diffusion transformer, for example, that is epsilon theta here, and that diffusion transformer going to predict the epsilon, and epsilon is the noise that you add on the forward diffusion process at each time steps t. So this diffusion transformer depends on t. T is the diffusion time, and the diffusion transformer should predict these errors, that Gaussian noise on each step t, each step time t here. That's the intuition. But you may like do an inference here. I mean inference, not the model inference, but you may infer this formula directly by, for example, maximizing the log likelihood of that process, because you know all probabilities there. So going further, so we discuss a little bit the diffusion transformers and so on. How the inference pipeline in diffusion, in, for example, video generations looks like. It looks like that. You had the video variational autoencoder. It's, one more time, the neural network that compress the video and form the latent space of these videos. But it's not only the compress, it has two losses usually. You had the reconstruction loss, yeah, so that means that you compress and decompress the video, and it's much better if this video after decompression, decoding, should be very similar to, not very similar, just the same. The best one is just the same video. And some regularizing loss on this latent space, because look, your diffusion transformer should be trained, learn the latent space, not the space of the video, but the latent space. But no one latent space is good for diffusion transformer. You understand, I think. So it's really a scientific problem of how you form this latent space. It's really nice research topics. It's not the obvious answer and obvious question here. So usually you had plenty of losses, not two, but these two losses are the main loss. So reconstruction and regularizing loss on the latent space. So you train this video via and you can use it. So after that, after you have the video via, what you should do? You had your prompt, text prompt, you pass it through the text encoder. It should be the, for example, just LLM, for example, doesn't matter. Some neural network that's modeling the text, modeling the language, and can give you embeddings of your textual prompts. One remark about that: in the last year, very popular is to take the decoder only large language models, moreover multimodal, so visual large language models. So like, for example, Qwen or GigaChat Vision, and do some process like a token refiner. So train some two layers or several layers after the like decoding layers of the Qwen, for example, to match with this diffusion transform. It's worked good. But you can take, for example, T5 encoder from T5 or BERT, or a clip. So what do you like for encoding the text? After that, you had the trained diffusion transformer in the latent space that can condition on these text encoder, on these text embeddings in the C there. And on the first step, total, I mean, just Gaussian noise on the same in necessary in necessary dimension, I mean, and do step by step reverse diffusion process because it's trained for do that. After you receive the latent of the image, you just use the video via decoder to decode this video, decode these latents to the video that you can show, you can see. That's how it works. How the principle, how the a lot of current text to video and text to image model works, and the diffusion process depicted there. So you conditioned on the noisy frames, text prompt, receive the less noisy video, and do it step by step. Okay, what's important in this process? Really important is compute. That's 3 videos that I most that I showed on to the listeners, because it's really, I think, how it's said. 1 minute. Sorry, don't know what's see there. It's really like touchable, because what does it depict? There is 3 models there. It's from Sora report. Here is 3 models: base model, little bit bigger model, and biggest model. All of that model is Sora, but the different size. They differ only on how many compute, equivalently how many GPUs, and so on, was used to train these models. So the same data, the same configs, and so on. Only differ is the compute. So that's showed how the scale is important, because model is the same, but this is just the small model, but it's not good. But that one is really nice. It's the Sora that we knew actually from public. During our experiments, we see the same. We had a lot of experiments on scaling now, and we see the same behavior of the model. That's really nice. I think in large language model we had the same actually, the same behavior, but video is more, I think, shows that in a more obvious way how the scaling is important. Okay, what else? How we can, I would like to talk a little bit about training approach of the diffusion transformers, especially. 4 aspects of that is really important if you want to train your diffusion transformer. First of all, I think the most important is that we had the standard like recipe of how we can train the really good diffusion transformer. We start from pre-train, as well as in large language models. What does it mean pre-train? Pre-train is the training on the huge amounts of raw video scenes and text descriptions of this video, text tag captions. Really big, huge amount. For example, I told about the movie again. They used for pre-train 400 millions, yes, video scenes. Do you touch? Do you like imagine how the amount of such data set in terms of gigabytes, for example? For 400 millions videos, it's really huge. It's you need like petabytes of storage, hard storage, to save this amount of data. It's more complex on several dimensions than, for example, large language model data set consisting only on text. After that, meanwhile, After that, you need to do a supervised fine tuning. But what do you mean? What do I mean that continuous training there? Because pre-train is not, like take a videos and just in like fixed resolution, and you receive the good model. This process is iterative too. So you start from, for example, from 256 by 256 videos. After that, you come to 512 by 512. After that, you come from, I don't know, 1K. And after that, you come to maybe bigger resolutions and so on. And this is like iterative process. So that's why I give here the continuous training. After that, you need to do a supervised fine tuning. Supervised fine tuning is a training, just training like in pre-train, with maybe small learning rates. That model that you receive on the pre-train on really clean data. That is, for example, marked up, annotate with artists, if you talk about the images, with some specialist of like doing and screening a film, if you talk about the video and so on. So you need really clean data, clean descriptions and clean and really nice looking videos. But after that, you need the LHF process. It can be DPO, it can be PPO, it can be, I don't know, direct reward tuning, whatever you mean. It can be, I don't know, another methods of like the training on the human alignments and human assessment with human, like, with human markups here. So all steps of this process is important. I showed the importance of the RLHF process when we talk about the C-dense and how it increases the video quality. That's really important. Another one is, I talk a lot about diffusion, but now flow matching is much relevant in my opinion, and a lot of starting from Sora, Clean, and so on, is not the diffusion architecture, it's flow matching architecture. It's some, in some sense, modifications of the diffusion, but I think so you had a lecture about the flow matching, so I don't stop on that. Another one that is really important in sparsity. Sparsity is really important because in the higher resolution, you have a lot of, so one video is such big bunch of information. So you should not model each connections. You should not like connect each pixel with each latent pixel with each latent pixel on the video to module this process, because in higher dimensions there are a lot of redundant information. So you can see from our experiments, we had a really nice Nabla method, but it's not published yet. So I talk about that a little bit later, I think, maybe on the next time. But from our point of view, in 1K resolution, from 80 to 90% of the connection is the redundant, so it can be omit. So it's, and without or maybe with less amount of like lose the quality. That's nice. That's important. Another one, the fourth one, is that you can see the current algorithm that I described. It's like, like vanilla diffusion. Is that you have, look, you have a 2 times there. You have a real time and you have a diffusion time. Yeah. So 2 axes. On the axis 6x, you have a usual time, just our regular time, and axis y, axis y, you had the noise or you had the diffusion time. You may do diffusion process simultaneously, you know, and this is a vanilla version. But you may think about and give such a observation that future frames can be, you know, can be denoised after the previous frames, because our world has the causal visuality, you know, because future depends on the past, but past, it's actually philosophical, quite a philosophical question, but past is not depending on the future. That's our world. So why we do simultaneous diffusion? We can do kind of autoregressive diffusion or causal diffusion. So you may denoise the future frames after the previous. That's nice, because that can give you ability to generate not the fixed on time number of frames, but like continue and continue to generate the next frames. So do not like have a restriction of the 10 seconds, that's all. You can produce a lot of a bigger video in terms of timing. So 30 seconds. After that, video of course degrade on the quality, but this is more stable version in the terms. Okay, another one is lost function. There are a lot of experiments, and we do a lot of experiments on loss functions. And I told a little bit later, before, when I talk about RLHF, for example. But you know, the diffusion touch with MSE loss, as you remember, I showed the MSE loss for you. And MSE loss is not good, actually, in terms of, for example, in terms of, I don't know, the common sense, because MSE is not good for images, actually. That's why we can use and try to use different losses. For example, perceptual loss, for example, adversarial loss. And adversarial loss is good, for example, in process of distillation of the models, such models, because main way to accelerate the video generation models or image generation models is to the diffusion distillation. What is that? You typically had a lot of steps from the noise to the good image. For example, 50. That's common. What if you train the student model to do the same process, not in 50 steps, but in 4 steps or 8 steps? So much less steps. If you do that, if you train such a student model, you can receive the final image not in 50 steps, but in 4 steps, in 5 steps, for example. So 50 steps versus 5 steps is 10 times faster. You understand? So you can accelerate diffusion models 10 times just simply by training the student. That's called the diffusion. And in that training of the student models of subjects, the student models, you can use the adversarial loss. So it's like you know, some flashbacks from generative adversarial networks there, and you can receive the good models there. So that's how, for example, Kandinsky flash was received. So the same, maybe a better quality, even better quality of diffusion model, but that's forward on 4 steps, that's forward on 50 steps. So 10 times faster. And that's as great for video too, because from now, if you want to generate, for example, 10 seconds video, you need to use one H100 during 10 minutes in inference time, I mean. So to generate 10 seconds video, you need 10 minutes. That's crazy amount of time, because user can forget that he would like to generate a video during 10 minutes, and after that he comes and said, I don't know this video anymore. So that's the diffusion distillation is the really key opportunity to produce and to create the model that can generate it much faster for 10 seconds for 1 minute, 10 seconds in 10 seconds, for example. That's not the reality, actually. There is such models. And third one about the losses, I mean, is the physics loss. That's quite difficult field, but physical inspired loss is nice loss too, because it's another way to train the models learn physics, such as RLHF, as I said. Another one is a video wire. We talk a little bit about wire, but one more time. If we use the image wire here, so it compress one, so do not compress in time, compress in 8x8 on heights and widths, doesn't matter actually. So on the spatial axis, number of tokens should be 1 million. That for 1 million for what? For 10 seconds in full HD or in HD. I think in full HD, but you may calculate if I had a mistake. So really huge amount of tokens. But if you train the wire that compress time axis by 4, you receive the only 200,000 tokens. That's quite better. 1 million versus 2 or 300,000. It's much better. But if you train the model on the with the 8 compression of the time, you receive 100 tokens. Is similar to large language models, and this is okay. For this is okay, this is okay, and this is much better, of course. But there are no one mod operational encoder for video that compress video in such 8 by 16 by 16 and not lose the quality after the training of the diffusion transformer. So that's this is the target, but not reality. But this one, these two compressions is good. Much better such a compression, 4 by 8 by 8. So the most diffusion transformers worked in slight and space that is received by data compression after wire. And the last important thing here is the data. You need a lot of data, as I said, to train to do a pre-train step of that. But you not only should download the data, you should filter the data. For example, estimate the complexity of the scene. You should estimate the aesthetic of the scene. You should calculate does video have watermark or not, and so on. So there are a lot of aspects that you should estimate, and the estimations is produced by another neural networks. For example, visual large language models or some convolutional neural nets. So that's important. You had a big amount of the video data. For example, 500,000. A lot of amount of the data. 100,000 10 seconds videos. But it's not enough. You should infer this data set with the aesthetics, with dynamics, with the complexity of the scene. So a lot of neural networks. Computationally, it's the equivalent to train computationally to filter the data set is just equivalent to train video generation models on such a data set. That's how it's important and how it's complex. After that, you should write the caption. That's really hard problem. because you train the text-to-video model, so in each video scene you should have each video scene should have the text caption for sure to train text-to-video. Yeah. So you need to apply visual LLM that is fine-tuned on video captioning, and you see 500 million data set. Each video send should be captioned, and on each video send you should apply the visual LLMs. So that's a crazy amount of compute to produce the data set. That's how it looks. And I see, I read there that only approximate from 10 to 20% of the initial data set is included to training data set. That's small amount. A lot of trash on the open source video in YouTube, for example, and so on. But that's illustration of how VLM doesn't matter which VLM. VLM write the caption to the video, and how human write caption, middle human, I mean average human, write caption on the image. I think that actually for me, the video captioning is the task that's performed by VLM much better than average person, because average here is captions from Lion. Lion is a really important data set. All models of text-to-image models before 2023, for example, were trained on the Lion, and the quality of captions you see of the Lion, and the quality of captions from VLM here, just usual VLM and just usual people. So that's really important. This one is really important, and because if you had the nice captions, your video generation models should understand you correct. You and your user, I mean, correct. So it's important. Okay. I talk a little bit about, to answer the question, world model or not. I give you the phrase from the Sora report. Sora report, I remember you the 2024, when they write that scaling video generation models is a promising path toward building general purpose simulator of the physical world. In another word, the world model. Of course, I show 1 minute. That's actually a report from Sora. Why it's not work? 1 minute. Sorry. So yeah, that's example that approve the phrase that I showed you before. But nice video actually. Nice peoples, nice movements, good visual quality, such as the film, I think. But reality, I mean, now is better. I showed you the sea dance examples and so on. It's really nice. It's much better. But Sora from December of 2024 was like that. So a lot of questions about the physics. I briefly tell you about some work about from ByteDance actually, researchers from ByteDance. ByteDance actually the really nice guys in terms of video generation. They had a lot of groups, research groups on video generation. Like I don't know how many actually, really a lot. ByteDance research, ByteDance seed, I think 3 or more, and all groups doing something on video generation. One of the group, especially ByteDance research, do the same, do that work. What is about? They simulate the 2D scenarios and train diffusion transform UNet, actually, not diffusion transformer, but it doesn't matter actually. I said you that diffusion transformer will be good only for scaling. For small models, UNet is better. Convolutions is better for computer vision and small scaling. They train the UNet on some simulated data set, 2D data set. And why? They would like to understand, does this UNet learn the physics laws or not? So that's interesting work. So the takeaways. So they consider 3 generalization scenarios: in distribution, out of distribution, and combinatorial. I said about that a little bit later. They consider 3 mechanical laws. It's actually the important laws. It's C, laws of inertia, Newton's second law. Actually, law of inertia, the Newton first law. So Newton's first, second, and third law, and the law of conservation of energy. So the really important laws of our world. They developed 2D simulator and implemented simple geometrical shapes, as I showed you before. They used UNet on different sizes to train, and they would like to answer a question: is it okay does this UNet really learn the physics? Does the UNet really understand the in classical mechanics, all process is described in equation, partial derivation equations, yes? So they understand how, does it understand this equation or not? Why it's important? Because if yes, you can apply these models, I mean UNet, diffusion models, in a lot of fields, in robotics, in self-driving cars, in movie production. Not, I think it's in movie production it's not so necessary. In hard time consuming process imitation, like steel preparing, for example. That's important. And so you can use this model in, for example, simulators for example, simulate some situations and train the robots, self-driving cars, on this synthetic data set. Because you are not afraid that is not bad data set, because models can understand physics, yes? And actually, there are plenty of works that can do the same things without the answer, yes or not. There are, for example, Gaia 1, they do a robotics task actually here, and not robotics, pardon, self-driving. They simulate the different situation, not do it by camera, but simulate. Because video generation can simulate whatever you want. If you train on the huge amount of data, it can imagine the car on the Mars, on the moon, in the Moscow, in the, I don't know, Harbin, in the Las Vegas, whatever you want. You can simulate what do you want, whatever you want, and can train your robot, your self-driving car on this data. That's the idea. And actually, it works quite. For example, we have a GR2 paper. It's a paper from, actually, I don't know from who, but I think by Dance too. They use interesting principle to teach the robot following the instructions. They do something like that. They had an instruction, they had the initial frame, and at first step, simulate the video during the instruction, and like that. Look at that example. You see, you had the initial frame and the instruction. Put the flower to the vase. So video generation model generate the video of how the hands take the flour and put it on the vase. And after that, robot just repeat this. So extract the trajectory and just repeat what video generation model said, the robot. And interesting result, and that's what they do in GR2. Interesting result that it worked. It has sort of result on the Kelvin. It's a prominent benchmark of the robotics task. It showed a good generalization to new environments, and they verified the scalability. So they in for the scaling laws. Only on 38 million videos for pre-training. That's nice. If you want to read a little bit more about that, about the Volt models, you can scan the QR code. So let's return to that work. Remember that work. So 3 scenarios: in distribution, out of distribution. I think it's totally understandable. Yes, what does it mean? It means that there is a test and train samples. Test sample is just from the train distribution. That means in distribution. Out of distribution, from the other distribution. Yes. Combinatorial is quite complex. I told you later what does it mean. So as I said, they use I had a mistake. They use a diffusion transform, not UNet. Okay. They had the stable diffusion variational encoder, but stable diffusion is a UNet, but they trained the diffusion transformer, not UNet. I'm sorry. So what does they simulate in the first experiment? They simulate 3 scenarios: linear motion, collision of 2 balls, of 2 objects, and the parabolic motion. What does it mean? It means that you throw the, for example, the ball, and the ball are going down on the gravity. Yeah, so the parabola, something like that. You can see the parabola here. This is collision of 2 balls. This is just linear motion. Or yeah, it's linear motion, it's parabola. And they sample 3 version of data set: 30K, 300K, 3 million. In the low resolution, actually. It's enough. It's enough resolution for the task. Only not 1K, but 100 by 100, 128 by 128. And they trained from scratch 4 models, 4 diffusion transformers. A small base, large Excel. It's you see the parameters there. So different size, the size of the model. The bigger model had 456 parameters, and they take this loss. What does it mean, loss? It's very simple. Your model produce, so it's trained to generate the videos. It can, after generation, you can measure the speed of the balls, speed of the balls, speed of the objects. And you measure the average error, I mean, just by module, L1 error of original velocity and the predicted velocity after the generation. So you measure the error on velocities. Understand? And this is not loss. This is error. This is error is the MSE actually. Error loss is MSE because of the diffusion, just usual diffusion. This is metric of quality, or it's error here, not the metric. One minus metric. And they see that interesting result that in distribution example, the model can follows and approximate the velocities very good. and error tends to 0 when the model is bigger and bigger. But in out of distribution examples, so when, for example, I don't know, it was a ball and after it goes to square, for example, or it was red balls, after that it's going to blue balls, for example, the error is not 10 to 0. That's actually not good, not good characteristic of that process, because for out of distribution result, in that easy setup, is that simple setup, diffusion transformers can like approximate the, for example, not for example, 3 laws here that is depicted here. You can see the examples. So this is out of distribution. So here is ground true. Oh, sorry. No, it's okay. So this is ground true. This is predict in distribution. Ground truth predict. You can see that it's just the same. Actually, it's really similar. But in out of distribution examples from the left, you see that common sense is okay. Common sense is okay because you see that, for example, collision. Yes, left ball comes to red ball, and after that comes from other side. But the velocity is not so correct because look, and the positions actually is not correct. So that's not good. So common sense is okay in that models, but prediction of the velocities is not okay. Actually, they consider the more complex scenario. What differ from the simple scenario? Because it's more complex. Look at that examples. They simulate a lot of things here. Not only the collision of two balls, not only I don't know, throwing the balls, and when balls come to as in a parabola way, they like use the fire simulator, as I said here, to simulate a lot of situations with a lot of objects inside of. So that's a combinatorial scenario, and they use a lot of metrics there, not such simple metric. As I said here, they use a lot of metrics after training on such a data set. It FVD, SIML, PIPS. It's more common metrics when we talk about the video generation models, for example, or image generation. And what they see that models tends to overfit on the training samples. That's not good actually, because the model is performed on out of distribution samples much worse than in distribution, even with the simple scenarios here. Here you see that if you showed this is actually the velocity. If you show the velocity in training sample from that range and that range, the correct prediction of and in test sample you showed the all range of velocities. You see that this region of velocity was predicted nice, and this region predicted not good, and so on. If you showed, for example, this and this, you see the like degradation in that field, and so on. That actually quite of understandable problem that each model can be overfitted. Yes, but for video generation models, and if we are talking about the generalization and knowing of the physics laws is crucial, you know, because we need video generation models to generalize on a lot of scenarios that never be seen in trained data set. But here some, you know, like not good result from that point of view. Moreover, models is overfitted on the shapes of the models, of the color, objects, color of the objects, and so on. But despite of these problems, video generator is still a promising way towards scalable world models. Because why? Because they take the simple scenario and they never used another scenario. So they train the model only on 2D simple forms, 2D simple laws, and so on. But when we train our usual video generation models, we talk a little bit. We had a much more diversity of the data set. So that's why the video pre-training is still promising way to receive the scalable world models, and we believe that we can do that actually. That nice links to read about. I think I share the presentation. What else about the world model? I hardly recommend to read the new NVIDIA Cosmos paper. They train several architectures, and they compare the autoregressive transformer to diffusion transformer in terms of video generation task. So they train autoregressive model like GPT to train to generate the video and compare to diffusion. That's really nice comparison, and diffusion is winning. Was winning actually. Moreover, they do a video generation model just by physical AI systems for robotics, for self-driving cars, and so on. That's really nice to read. Moreover, do anyone see or read Neural OS? Nice. It's the paper towards, I think, world model too. World is the operation system. So what's authors, researchers do in that work? Did in that work? They do the funny thing actually. When you operate with the computer, so work on the computer, you actually see only pixels on the screen. Yes, only pixels on the screen. You understand that there is some file manager inside of some operation system, inside of some hardware inside of, and so on, some transistors, and so on and so on. But the output is just pixels on the screen. So the author said, if the working with the computer is just a pixel on the screen, so as a video, why we not directly generate the videos and like on what was seen on the computer when user works in. So, and they do the same thing. They train the diffusion transformer on a lot of huge amount of the video of the like sessions, and they receive nice results actually, because you see here is just the generation. So you can manage this system by mouse and the keyboard. So it's not a video completely. So you can manage the system by mouse, for example. So you can click on the home on the Firefox, and frame was generated not only by previous frames, but by previous frames and some clicking of the mouse, and for example, some putting the key on the keyboards, and the system not perfectly because it works slow, but it's nicely operates with such an initial information. So it's generate the nice session. So I think that it's really interesting works, at least I should I highly recommend to read this paper. So okay, few words about the our latest model, Kandinsky 4. Okay, yeah. About the Kandinsky 4. I think 5 minutes is enough. Kandinsky 4.1 and what this model can do. We train, as I said before, we train image generation models, video generation models, and first of all, image generation. That's a diffusion transformer. We apply and do a pre-training. We apply the supervised fine-tuning. Not RLHF till now, but we highly experiments with RLHF. But we see the nice quality after SFT, so we can improve the prompt following, improve the visual quality, improve some really important objects and concepts, because we represent and do a Russian model, so we should know the Russian cultural code, for example, some Sber characters, and so on. And we knew that. Moreover, because Kandinsky is integrated in GigaChat, you can just write a prompt in dialog format and edit the image, for example, in the way you would like. Moreover, we can generate a text on the image, so that's a common, I think, property of such models. And we had our own benchmark. We had that's the results on our own benchmarks that created by my team and team of validation. Sber. They divided by a lot of categories, like aesthetic of the image, location, and so on. A lot of categories. And on such benchmark, we see that Kandinsky 4.1, pardon, is nice model. We are going to improve this model, and in a journey, it's our conference in November, we present the new family of the models, Kandinsky 5. So see what we can do more. We can do in painting task. It's when you generate not only from the total noise, but from some region that is already filled. That's how you can model the generative Photoshop, for example, here. Moreover, we had a team, special team of the Sergei Markov. They can do the editing, pixel-wise editing task called Malvina. Do you heard about that? No? Okay. What's the point here? It's the point that it's a Photoshop actually, but Photoshop not in terms of the mask, as I said, but in terms of the instructions. So the reason that you would like to edit the photo just using the word or text, no more, because text is much more simple input for people, for the humans, not masks, not so on. Architectures is the following. You can see that use a GigaChat vision. They use the fine-tuning image-to-image diffusion models, and they fine-tune the whole pipeline, whole ensemble on the editing task, on the highly detailed, highly high quality editing pairs of the two pictures and instructions that describe what you should do with the first picture to receive the second one. A little more examples there. Okay, about the video. Just the same, actually, we are going to improve the prompt following, visual quality, dynamics of the video. And this is just a few examples of the text-to-video task here, of the image-to-video task. Oops, sorry. I talk a lot about how we can do this architecture and some aspects that is really important. Moreover, we can like control the camera movements, for example, turn around videos, zoom in, zoom out videos, and so on. And this is received simply by training the LoRa. That's funny. Moreover, we improved understanding of the physics. And this why we developed the RLHF procedure there and some special reward functions. We had a lot of benchmark that's really nice. And I see it's really popular kind of video. So sorry, there is a sound beside, but I don't know what's happened with the video. But Kandinsky cannot generate audio simultaneously with video by now, but we works on the task too. Moreover, we had the Kandinsky 3D is the modification of the model that can produce the mesh based on the prompt. So you can generate an image or 4 images from 4 sides and then 2D to 3D, do a 2D to 3D task to manage and create the 3D model. So a little words about the applications. There are a lot of applications actually of such models. For example, for design, it's our case from DomClick when you change the design of the interior design. Case from DomRF when you change the exterior design, so design of the building. Nice case with Samocat when you our Ecom daughter of this bear, when you just take this photo after that do image to image to generate the background with the objects and then like given a life. Do some nice design of the cars. Do a lot of collaborations with museums, for example. To, for example, alive the images. See several examples. Do a nice collaborations with Pushkin Museum, for example, that the original picture of Lucas Cranach, and this is like extended by extended picture by Kandinsky in painting, as I said. Why extended? Because it's not it's original, but the experts said that it's not the full image because the Madonna is not on the center but on the right side. So experts thought that the original picture is cutted during, I don't know, one process. Some nice collaborations with, for example, Soyuz Multfilm. Nice collaborations with GigaChat and creating the avatars because you can write you can create the character that you can talk with, but it's much better that character had the face, yeah, and can communicate with you. So thank you. That's my contacts channel and so few questions, I think. Okay.
Uh-huh. Oh, thank you for the lecture. Just a few questions. Maybe I missed this part, but could you slightly more elaborate how do you evaluate video generation models and benchmarks? And this part is not really straightforward, it seems.
Yeah, sure. There are at least 3 ways of how we can generate, how we can estimate the quality of the video generation models. First one is just side-by-side comparison. For example, Video Arena as I said here, is a side by side. All right, not side by side, but human evaluated. So that's it's very similar to understand actually how it works. You had several questions. A lot, actually, a lot. Not only you cannot estimate the video quality just by asking one question, because there are a lot of aspects. So because the video, first video, if you compare first and second video, the first video can be better on, I don't know, the prompt following, but can be, and second video can be better in visual quality, for example. The third video can be, I don't know, better in terms of dynamics and quality of the movements. So you should ask a lot of questions actually about the text prompt following, a lot of questions, because there are many aspects. So a number of objects from the prompt, properties of the objects, and so on. Second category is like questions about visual quality. Third one, questions about dynamics, about the quality of movements, and so on. In our benchmark, our own benchmark, we had near 20 questions to compare to two videos. It's really hard to like, for example, you had like, for example, buckets of 2000 or not 2000 videos. For each video, you had like 20 questions, you had 60 annotators. So like you need like 2 days to estimate which model is better.
So may I then ask a following question?
Yeah.
Okay, this part is
So
clear.
this is okay. 1 minute. Second part. So this is side by side, human annotated. Another one is the AI evaluation. What does it mean? So model evaluation. So what does it mean? It means that you can train some models to estimate the quality of the video. For example, you may apply the object detection model to understand in which video is much more is more convenient, for example, to the prompt in terms of number of generated objects, for example, yeah. Or you can tune the visual language model to understand, I don't know, the different aspects that is presented on the generated video. Or you can use a clip score, for example, or clip model to estimate the like how video or image first frame is corresponded to, is far from text. So that's the second. So side by side human evaluation, model evaluation or AI evaluation. And second one is like semi-automatical metrics. Is like, you know, we put on the public Kandinsky 4.1 and ask the people, is it better than Kandinsky 3.1? People said, yes, it's better in the public release, I mean. And this is semi-automatical metrics, is like product metrics. That's nice too. So 3 kind of metrics that you can manage there.
Yeah. Thank you. Thank you very much. It makes the situation much clearer. And during the development stage, because as I understand, all these metrics takes a lot of time, except automated like model-based evaluation. And what do you use during development stage?
We use human eval and AI eval. We use AI eval for each step of the video training. So there are a lot of benchmarks actually. Not a lot in compared to LLMs. And LLMs is much more benchmarks. But in the video generation, there are plenty of benchmarks too. For example, for image, it's GenEval. For video, it's for example, what is a good benchmark for video now? vBench 2.0, for example, is the last one. It's better. But they all had their own pros and cons. Actually, it's not it's not good in all aspects actually. But we, despite of, we evaluate the model on such a benchmarks and see we see the train loss, how it go down, and we see how metrics on that benchmarks is grows up. We see that, but it's not enough. During the training, for example, 2 days, every 2 days, we do a small human eval, actually developers eval. We had a small bucket, developers bucket, and we had just 3 questions: prompt following, visual quality, dynamics quality. And usually, I usually do the task. Here I see Maria Lev do the task a lot. And we see, does it correlate, these AI developers eval metrics correlate with AI eval? And we see that a little bit. But developers eval or human eval is important. But after that, after the training is completed, I mean, after the pre-training stage, for example, we do a big human eval, not only by developers of the image or video generation models, but by 100 people, for example, like professional markuppers, annotators, I mean. So that kind. But after we release the model, we see on the product metrics. As I said, the semi-automatical metrics, because so that's represent how it's seen in public. So that's important metric too.
Thank you very much. Thank you.
Okay. Yeah, one more time. That's contact. Last question. Yes. So I see the.
Hello, thank you for your presentation.
Thank you.
I have a question regarding the data which is used for training these models. As far as I understand, as far as I know, synthetic data is frequently used for training generative models. But I'm curious about the reason for this. Is that because real data is not enough for training such models, or synthetic data is by its properties is just better? Can you please answer this question?
Thank you for your question. That's a nice question, I think. I show one more time this picture. We train actually on all data set for training is synthetic in sense of text. You don't have the video actually in internet, so scene, 10-second scene. That is comes with the text prompt, with the description. There isn't any descriptions of the scene, even for not scene, even for videos, because in YouTube, for example, you had just a video. Video maybe names, title, and comments. That's all. So you don't have the full description. So our whole data set is synthetic in terms of the text. So each text synthesized by VLM, but video is not synthesized. Image is not synthesized there. And I said about the quality of the human in large scale. I mean, average human caption and VLM caption. VLM caption is better. VLM caption is better in compared to average P. Of course, you can like take an artist and give him a task to describe the video and the image in details. He write the better better caption than the model. But in terms of average people, the model writes a much better captions. So that's the first part. About the synthetic in image and video, that is your question, yes?
Yes.
It's not actually correct, because researchers try to prefer the not synthesized image and video. They prefer real scenes that is taken from the camera or iPhone, for example, smartphone. But if we talk about the refining or alignment, or especially I mean SFT and RL, you may use if you want to, for example, to create the aesthetic tune of the model, you may scrap the mid-journey, for example, images, and do an SFT process with just mid-journey images that is highly aesthetically looks like. You know, that's some engineers do the same thing, but I think you may do and receive the aesthetically look like model without mid-journey, for example, and without any techniques like that. But it's not like crime to do that. But in pre-training stage, in terms of visual content, engineers, researchers prefer the real scenes, not synthesized, not synthetic.
Okay, thank you.
Thank you. Thank you.